What happens
When an unstoppable force meets an immovable object.
On the 23rd of March 1962, an English chemist called Neil Bartlett was about to find the answer to this question using chemistry. The unstoppable force in this case was platinum hexafluoride, perhaps the most powerful oxidizing agent ever discovered. And the immovable object was xenon, a noble gas known for being completely unreactive. An accidental discovery had led him to try this experiment, and what he was about to discover would change chemistry forever. The noble gases, helium, neon, argon, krypton, and xenon, had been discovered by some absolutely brilliant work led by Sir William Ramsay around the turn of the 20th century. I mean, think about it. How do you discover elements that are completely unreactive? How do you even know they're there if they don't do anything? Well, for a man like Ramsay, anything was possible. I strongly recommend checking out my video on this incredible achievement, which I'll link below. In 1913, the Danish physicist Niels Bohr proposed his theory of atomic structure, with the electrons arranged in shells around the nucleus. 3 years later, the American chemist Gilbert Lewis and the German physicist Walter Kossel took this one step further to examine what happens when atoms bond together. They proposed that atoms are most stable when they have a full outer shell. So, when they combine, they either transfer electrons to form ions or share electrons to form covalent bonds, giving them a nice, stable, full outer shell. That's why atoms react with each other at all. That's why chemistry exists. But this is also why the noble gases are so unique. Unlike every other element in the periodic table, the atoms of the noble gases already have a full outer shell, so they have no need to react. They just float around as individual atoms, not doing anything. Because of this, for decades, every chemistry textbook insisted that the noble gases were utterly inert. Still, a couple of scientists had wondered if there might be a way to force them to do something. To understand why, let's compare two noble gases, neon and xenon. The xenon atom is much larger than the neon atom, which means that its outer electrons are much further from the nucleus. This means that there's a much weaker electrostatic force of attraction between the positively charged nucleus and the negatively charged outer electrons. So, in theory, it should be easier to remove an electron from xenon than it would be from neon. You just need to find something reactive enough to be able to rip an electron from xenon. The energy required to remove an electron is called the first ionization energy. As you go down any group in the periodic table, the first ionization energy decreases because the atoms get bigger. Because of this, in 1916, Kossel theorized that the heaviest noble gases, like xenon, might be able to react with fluorine, which is very good at removing electrons, to form fluoride compounds under extreme conditions. In 1933, the American chemist Linus Pauling went further, even sketching possible xenon-fluorine molecules. But these ideas were still only speculation. Without an experiment to prove it, the inert gas law remained unbroken. In the early 1960s, Neil Bartlett was a young chemist at the University of British Columbia when he accidentally stumbled upon a tantalizing clue. His work focused on the chemistry of fluorine. Fluorine is the most powerful oxidizing agent of any element in the periodic table, meaning it's the best at removing electrons from other atoms. However, even fluorine was unable to oxidize any of the noble gases. One day, Bartlett and his graduate student Derek Lohmann were experimenting with fluorine and platinum. Platinum is a highly unreactive metal, often described as a noble metal, although it's still more reactive than the noble gases. Whilst experimenting, they accidentally produced a strange, blood-red solid that they'd never seen before. After a lot of analysis, they eventually figured out what had happened. During the reaction, they had formed a gas called platinum hexafluoride. This wasn't a new discovery, it had been made by other chemists a few years earlier. However, during Bartlett's reactions, he had inadvertently allowed some oxygen to leak into the apparatus, which reacted with the platinum hexafluoride to produce the red solid, which they identified as an ionic compound with the formula O2 plus PTF6-. Now this was astonishing. Let me explain why. Like fluorine, oxygen is a very strong oxidizing agent, so it normally takes electrons from other things to give it a negative charge. But here, PTF6 had taken an electron from O2. creating a positively charged O2 plus ion. Bartlett realized that PTF6 must be an even stronger oxidizing agent than oxygen itself. Bartlett then checked the numbers. He saw that the first ionization energy of O2 was almost the same as what had been calculated for xenon. In other words, O2 and xenon were essentially equally hard to ionize. He realized, if PTF6 could strip an electron from oxygen, why not try it on xenon? It was a wild idea, but the numbers said it might just work. Bartlett was working late on Friday the 23rd of March 1962 when he assembled a simple glass apparatus. One side contained the deep red PTF6 gas, and the other held colorless xenon gas, connected by a thin valve. At around 7 p.m, he stood before the experiment, ready to test what happens when an unstoppable force meets an immovable object. He reached over and flipped the valve open. In an instant, a reaction occurred. A solid orange-yellow precipitate formed at the junction of the gases. Bartlett instantly knew that he had violated a sacred law. A noble gas had just done something chemically impossible. Bartlett later wrote about that moment. When I broke the seal between the red PTF6 gas and the colorless xenon gas, there was an immediate interaction, causing an orange-yellow solid to precipitate. At once, I tried to find someone with whom to share the exciting finding, but it appeared that everyone had left for dinner. He described the whole thing as happening in the twinkling of an eye, and how it was extraordinarily exhilarating. Bartlett pressed on with more analysis. That orange-yellow solid was subsequently identified in laboratory studies as xenon hexafluoroplatinate, the world's first noble gas compound. Just 8 years before this discovery, the English athlete Roger Bannister became the first person ever to run a sub-4-minute mile. Long thought to be impossible, within months of Bannister's achievement, other athletes around the world managed to achieve a sub-4-minute mile as well. Bartlett's achievement was the chemistry equivalent of the 4-minute mile. Once he showed that the impossible was in fact possible, the floodgates opened for other chemists to make similar achievements. Chemists rushed to push the boundaries, and a series of xenon fluorides were made, as well as compounds of krypton and even the radioactive radon. The old inert dogma was officially vanquished. A whole new field, noble gas chemistry, was born. Today, well over 100 noble gas compounds are known. These once-shy elements have real-world applications. For instance, xenon difluoride is used in making the chemotherapy drug bifluorouracil. Excimer lasers use compounds of argon, krypton, or xenon to emit intense UV light for precision eye surgeries. Even the radioactive gas radon, once considered a hazard, can now be chemically scrubbed from mine air using these new reagents. All of this work traces back to one quiet evening, one empty laboratory, and one chemist willing to trust the numbers more than the dogma. So the next time you think that something is impossible, just think about xenon. Maybe the strict rules that are holding you back are just something that you've been telling yourself over the years. Maybe, when you really think about it, nothing's holding you back at all. Let me know in the comments if there are any other stories you'd like me to make a video about, and if you made it this far, please consider liking and subscribing. It really helps to tell the algorithm that this video is worth watching. Also, if you'd like to support further, check out my Patreon for bonus content. Thanks for watching, and I'll see you in the next one.